Hello, good morning again. Welcome to another session of our very exciting AI class, right? And today I want to start maybe a kind of like a mini series on the path toward my end goal, which hopefully I can make it happen this year. I want to talk to you about the language model because it would be a crime to humanity if I don't teach you this about LLM, the large language model. And in order to go through that, like ChatGPT, like inner working and stuff, we gotta talk about the artificial neural network first, okay? So just to let you guys know that I'm actually skipping like a huge chunk of machine learning materials that I used to teach last year. It's about making sure that you can trust your results. It's called like all these validation results. Like remember that I was telling you that when you split your data, you don't do just train and test. You do like train, validation, and test data. And this kind of whole process will make sure that you can confidently evaluate your model. And that is actually quite a big thing in machine learning. I'm actually skipping all of that. So I guess if you are doing machine learning for your research, you do need to know about validation. So maybe you can review the last year materials, or I don't know, come talk to me if you need some guidance. But today I want to start on the neural network so that I can go through hopefully language model in the end. So we only have three classes left, okay? All right, so when we talk about machine learning, there are something called state of the art. So that's the term for something that's like the best in the field. And there are two types of data. So if your data is inhomogeneous, that means that you have columns of features that might be strings, might be like numbers, might be classes. So data that are mixed, for example, usually think about the real world. You want to predict customer preference. Customer has weight, has height, has like spouse, education. So all these things, it's not in the same type of data, right? In the end, it has to be number, but it's not the same kind of categories of data. So that's called inhomogeneous data. And I guess the best model you can use today is gradient boosting machine. I didn't go through this one in detail, but I mentioned it before midterm in the lecture that I record for you. And these are the big hitter in the field: XGBoost, CatBoost, and LightGBM. So feel free to explore into that if you really need to squeeze like the last performance out from your data. These things are built for that, okay? But then there are other kinds of data that are homogeneous. Homogeneous, the first thing that artificial neural network do really, really well is image, right? Think about image. Image is pixel. A cat picture that is, I don't know, 128 per 128 pixel wide, width, and height. It's just a bunch of number from 0 to 225. Well, actually, it's come in three numbers per pixel because it's a color. But again, these are just a number that goes from 0 to 225. They are homogeneous. They're the same thing. So your input to your model is just the number that represent the brightness or the pixel, the grayscale, the level of display of that particular pixel. Like they're all the same. So that's why it's called homogeneous data. And that is where this thing shines. Okay? And artificial neural network, it's the kind of like the first iteration of that kind of architecture that deal with homogeneous data. And now you can probably like have seen some of these terms like deep neural network, right? Convolutional, LSTM, and transformer. So in the end, if I can get to this, we can talk about ChatGPT for real. It's good to know like what is ChatGPT built off on, like why is it so good, right? And that is where the transformer network, like it's a, I guess, big new thing. Well, not new anymore. It's like 7 years old now, but it's 7 years old in AI landscape. It's ancient, okay? All right, so we're going to start from the beginning. Okay, so first, let's say you have data like this, x and y, right? And then it has some noises too, right? You see that data is actually fluctuated, like it has some width into to the line, so it has noises, right? So how do we fit a line to this data? Okay. So first, if you want to do anything to fit the line, the general concept is called function. Right? A function is just something, it's just a black box, right? That given x, you get y. Okay, think about function like this. And then there's nothing magic about ChatGPT, right? It's the same thing. ChatGPT is just a function that you input something, it spit out something. That's all, right? But in our case, a function can be just, like y is a function of x, right? And you can come up with, like a principal way of doing that. For example, you can do like polynomials, right? That's something you've been taught for a long time. Maybe you can do sinusoidal because you have some ups and downs, right? You can do that, right? Or if you don't know what form to, again, like these are what I say principal way of doing, because you gotta have to have some prior notion of what this component is doing. And you kind of guess, right? Like if I were to have the combination of these components, it should produce me, some sort of things that look similar to what I want in the end. But what if your function is so complicated, like the things that you want to fit, it's so complicated that you cannot even, like you don't even know what this looks like. Like it comes in like multi-dimension and like it's so complicated. And another thing is you don't even know like which function to use, like which component are you going to use. Then this is where this thing shines, right? Artificial neural network, okay? So think about it, it's just a function, right? But it's a function that you can kind of customize things in a great detail. And it can, I would say, like, if you give it enough parameter, it can do everything that you want. So that's why it's called universal approximators, right? It can approximate everything. If you give it enough power, like throw it enough compute into it, yeah, it would reproduce something that you want, right? Okay. Another thing that you can think about is it's like a Lego. So when you think about how to build the artificial neural network, it's or like deep learning and stuff. There's a bunch of building blocks that you need to know, and you can compose things together. So one of the things that I find quite challenging when I read student paper, proposal is that they usually say, I want to use ANN. And that's so vague because ANN can be anything, like it's too vague. So usually if you want to use ANN, you might need to scope down. It's like, okay, what building block are you going to use? Like what type of layers and how much compute you want to, so that's kind of thing. So when you talk about ANN, it's so broad. So that's kind of thing too. Okay, so what kind of things that you want to consider is like kernel, activation function, architecture, optimization, regularization. So there are a bunch of things that you can do in order to make it work. Okay, so that's where the complications come in and all this, like technical jargons comes down to. Okay. And you might be, you might take a notice on the term itself, right? Neural network, right? Neural network, it has some connection to biology in the neural cell in I don't know, our body, right? And that is actually how this architecture was inspired by in the early days, right? So as you can think about, I'm not a biologist, but I read about it, and like when you have a cell and the cell has some signal like input, and then it do some transformation to the input, and then it send the signal into another cell, so it has like an architecture of a neural cell that process the data in a certain way, and that's how this architecture inspired this type of like mathematical functions in here, right? But I just want to let you know that this type of connection is actually not being used nowadays. Like nowadays, when you even think about ANN, like the term's still there, but ANN nowadays doesn't really have any meaningful connection to the biologies anymore. And actually, if you try to make your ANN mimic the biological working, it actually hurts your performance. Like you just think about it's just another type of function. Think about this as just mathematics. I think that would be the best way. Like it has no connection to biology anymore. Okay. Right. So what's the architecture on ANN, right? So we think about it as like a little building blocks. So this circle is a node, okay? And again, when I say about like this entity, this is just a function. So these are small function, easy function, all of this, right? They are functions. And you can come up with, any number of nodes, doesn't really matter, right? And the way that we organize this ANN is in a layer, right? So the layer is just a function that, kind of receive concurrent inputs. That's all it's doing. Like actually the layer, it just helps us visualize it. Like in the end, this is just the order of operations in the function. That's all. It's like you're putting parentheses in a different function when you do the calculator. That's all it's doing, okay? So when we think about this type of architecture, we'll have something called layer. Okay, so the first layer is called input layer. So and as you can imagine, this function receives the input from your x, for example. Okay, and it just do something inside, right? We'll skip it for now, and then we're gonna go to the output layer, right? So output layer is a function that output something that you want to predict, right? And in this case, you want to predict two things, 2y, okay? Like if you want to predict one thing, like for example, you want to do forecasting with just one number, then you only have one node. If you want to predict 10 things, just have 10 nodes. It's really, really flexible. I guess that's another thing I like about it. Like you want to predict 20 things, just 20 nodes. That's all you need to do, okay? Okay? And then next stop is something inside. So these are kind of like the actual kind of like brains of it. So this function is actually not that much different from these functions in here. Like they're a little bit different, but they are the same essentially, right? But inside we actually have a lot of them inside, and these are all the hidden layer. Okay, so these are the first hidden layer because it's the first one that in the sequence. And then this one is the second hidden layer. And you can have more. And then I guess if you have a couple more, then we start to call it deep learning, just to get like our project more sexy naming. That's all. But so when you say like I do deep learning or like deep tech, I don't think if you just come up with a way to do maybe 10 layer deep, then you can call what you're doing deep learning. It doesn't really matter. Okay? So I want to start with what happened in the hidden node. So maybe like this guy here, because the rest is the simpler version of that. Okay? So think about this again. I want you to internalizing this as the function. So when you say function, that means that this is just equation. This is the math equation. It gets some input. Actually multiple input, okay? And it can produce multiple outputs. Okay, so that's all it's doing. Lots of inputs in it, and lots of output going out, okay? And that is what I'm doing here, right? You have lots of input, you have lots of output. Okay? All right, so what's happened inside? It's a mathematical function. There are two things in here. First, this guy right here. First function, and then the second function. That's all. See, this is really powerful. I don't know if you're surprised by this, right? Because if you never heard about ANN before, or you never really see what it's doing, you might think that it's like, oh, this is so complex, right? But in the end, ANN is just a bunch of really, really simple function. But its architecture, that's what makes it so powerful. Okay, so what is it doing? Okay, first, this is just linear combination, right? You have x, okay? When I say x like this, there are many x's, right? So I'm going to write it as just a big X. So that's the vector, okay? And also, when you have the linear combination of things, you want to combine x with different weights. And the weights is something that you will train for eventually, right? So this weight will get written into the weight matrix, weight vector, right? When I do x dot w, that means that I'm doing the linear combination of your input and the weights, linear function, right? And I'm just adding something called bias. So bias is almost like y-intercept. It's just adjusting the whole thing up and down, per se. Okay. I just want to mention that you actually have seen this before. This is perceptron, like the very first class that we talked about machine learning. We talked about perceptron, and I was saying like perceptron, it's just a straight line. This is exactly what it's doing. Like it's the same thing, okay? But then if you only have the linear function like this, your function, your whole architecture will not be as powerful. You need something non-linear. That's why you get something called activation function, okay? Do not let the name intimidate you. Activation function come from the term that is actually relating to biological, because the cell will send the output only when it's activated. So like biology terms. That's why the terms come in here. It can throw people off, like what is activation? That has nothing to do with math in here. Think about this as the nonlinear function. And I think it will make more sense in the long run in terms of other architecture. It's just something that gives curve to your prediction. Because without the activation function, you can only predict straight line. That's all. You need something curved, you need something nonlinear. So that's the point of this activation function. And you can choose what you want to do with it. You can choose the type of activation function, right? And that will affect your, the performance and and other things down the line, okay? And once you put the data through the activation function, then you can output your data. Notice that when I output my data, this activation function only output one thing. This is scalar. When I say scalar, it means just one value. It's not a vector, right? You just copy your value over and this one output three things, but it's the same three things. It's just repeating the same value. Because this one is actually connecting to a lot of nodes in the other layers. That's all it's doing. Okay? So first, I want you to not get intimidated by the math, because there's nothing really in the math. It's just that one. That's it. Like your, middle school math can understand this. So nothing complicated. The complication comes from all the little techniques that people have developed in order to make this one work. That's where the complication comes in, okay? All right, so I talked about this one, but the same thing that I talked, the same concept applied to all of these nodes in the hidden layers, okay? And you can have more if you want. Okay, next up, I already compared with perceptron, so yeah, just want to kind of hammer this point down a little bit. All right, so the input node is actually even simpler, right? I'm talking about this guy here, input. Okay, what's about the input? Input is easy because you don't have to have, right here. You change this one, okay? So the input node only accept one input, because if you have multiple input, you're supposed to have multiple input nodes. So the input node expects one input, so just one x. And you don't even have to do the weight. There's no weight. Weight is 1, bias is 0. So just a mapping function. Essentially just doing nothing, but I just want to write it in terms of the linear and nonlinear part. The linear part, do absolutely nothing, right? And the nonlinear part, just do absolutely nothing too. See, this is just one-to-one function. So essentially, I can just even bypass this thing, but people write an input node so that the library know how many inputs it's expecting. So the input node has no weight, nothing to train. It's just there so that the architecture falls into the same pattern. That's all. Okay. And also single input, single output too. Okay, just one and the same thing go out. That's what it is. Okay, so this guy right here. Okay. The next guy that I want to talk is the output layer. Okay, output node. The nodes in the output layer. Okay, a little bit more complicated, but simpler than the hidden nodes for sure. Okay, so first, the output node will get a lot of input because it has a lot of hidden nodes behind it, right? So it gets a lot of things from it, right? It does have weights into it, so you got to train, right? It has some bias that you need to train, right? So you do the again the linear combination of the input with the weights, okay? And then, but the easier thing is that the activation function it's linear. It's just mapping one to one. So there's no nonlinearity in the output node. It's just linear combination of your input, okay? And then it outputs a single output, okay? So that if you need more output, you have more output nodes. That's how you design it, okay? Right, so far so good? Okay, so let's start with the simplest ANN that we can think of, okay? That's gonna be the architecture with one input node and one output node. Okay, there's no hidden node in here. There's no hidden layer. Okay, so let's think about this. This one looks more complicated than it should be, but stick with me because we'll get more fun later. Okay, but think about the input layer. There will be in all the nodes there will be the linear part and the non-linear part, right? Same thing with the output layer. There will be linear and non-linear parts, right? So the linear part in the input node do absolutely nothing, right? And then the non-linear part also doing absolutely nothing. So that's why if I input x into my input layer, the output is x, and then again x becomes z in, and the z in become phi out. So essentially what I'm doing is like the output of this is the same thing as this one. That's all this one is doing. Okay, same thing. All right, and the output layer will just do this part that is a little different. So this part has weight and bias. So that means that my input, which is phi out, will get multiplied by the weights and added to the bias. So then my z out become my y hat. So that's my prediction. Okay. But again, if you were to combine, all of these intermediate steps into one equation, which you can do, you can keep substituting everything back, you end up with this one. And this one, you might recognize, it's just a linear function, right? It's the output, it's just the weight times the input plus y-intercept. This is linear, this is a straight line, right? And if I were to fit this equation, this artificial neural network, like to my data that I mentioned earlier, this is what I get. Like I use Python library that we're going to use today to fit this exact architecture to that line. This is what I get. This is the best fit that this network can do because it can only do straight line. But I mean, it makes sense, right? If you were to do linear regressions to this data, this is something you would get to. Okay, and in every model, something that you should keep an eye on is called number of parameters. Okay, the number of parameter is anything that you need to train for. For example, in this architecture, something that you need to train for is weight and bias. The rest, there's nothing to train. It's just a number, right? This one, weight equal to 1, bias equal to 0. So no need to train for it. You need to train for this one. So in the end, you have 2 parameters. Okay. And the number of parameters will determine how complex your architectures are. And this is exactly what I ask every student. Like, what is your, when they say you want to do ANN in their research, what is your estimate of parameters that you want to use, right? That's something that you can I mean, if you use the Python library, it will tell you. But that's something that you need to kind of have a ballpark on. Or else it can go as crazy, or it can go as simple as this one, right? If you were to use two-parameter network to fit your data, you're essentially doing ANN, but your ANN doesn't work at all. It's just straight line. So something to think about, right? When you propose to your advisor or something, like think about how complex you want your model to be, like something that you can think about, like after this class, obviously, right? Okay, let's do something a little more fun. So this one, I just add the hidden layer. That's all, okay? So the input layer is the same. So when you go, X goes in, the same thing goes out, right? For the hidden layer, it's a little more, involved, right? You do have something to train for, right? And you also have the nonlinear function. So this one is a classic nonlinear function called sigmoid function. Let me show you what it looks like. Okay, that's all. That's what it looks like. So sigmoid function is a function that takes in whatever input. Your input can go from negative infinity to infinity, but the output is only going to be capped to negative 1 and 1. And why are they choosing this? Purely mathematical tricks. Because artificial neural network so complex, right? And if you have function that can output a lot of things, it can make the numerical unstable. So they want a function that they can be safely, certified, making sure that at least if something crazy goes in, you're not getting some crazy number out. You only get from negative 1 to 1. So it makes your calculation kind of stable, per se. That's the mathematical tricks. That's why they're using that. But you're gonna see that next time, this one is too safe. We're gonna be more adventurous. So we need some risks in order to make our network learn faster. So this one is too safe. Sometimes it makes the network too stupid because the number is capped. So nothing gets learned. You gotta take some risk, man, in order to get some better results. So we'll get some more risky one next time. Okay, it's called ReLU.
แต่ว่าเราไม่ว่าเราจะได้ data รูปแบบไหนก็ตามมันทำให้อยู่แบบอยู่หน่วยเดียวกัน
Yeah, she was asking about is it the same as normalization? Yes, but there is actually the normalization function that we can use. It has different ways of doing, but essentially the same. Yeah, you're correct. You're correct. With this particular function, it's almost like normalization. But I would say that this one maybe what I would say would be more like capping the value, because this one doesn't. I mean, if you are going in from the value that are around 0, the value that you get out it's about the same magnitude. But then if you come up with something that are very, very negative and very, very positive, then your value get capped. So because normalization means like you scale everything down in the same scale. That's called normalized, right? But this one is more like if you are too high or too low, you cap the value. So maybe just like normalization, but not exactly. But we do have normalization steps later on for the image. Okay, but thank you for asking. All right. And you will see that the math is actually not that bad at all in everything relating to like this neural network. Okay, so that is the sigmoid function. Okay, and once we got the output from the sigmoid function, then we go to the output layer, which is only has the linear part, right? So you only have these two things, right? So, all right. So if I were to count right now, like how many parameters can I do have in my neural network, then I would say 1, 2, 3, 4. So that's the complexity of our network, okay? And if I were to write everything out, this is the function that results in the end, combining all the intermediate steps. As you can see, that this one is non-linear, right? And that's why if I were to fit this, I get a better result. Like, but not, I mean, I guess this is there's only 4 parameters, so I can do more. And that's exactly what I do here, okay? And it just gets crazy to write now, so you can have to imagine the steps that I did again, right? I mean, technically, I mean, I can always write the whole equation down, right? It's not magic at all. I can just write what happened inside mathematically. But it just gets too cumbersome to write. That's why you can have to imagine what it looks like, okay? Okay, so here I have one input, the one node in the input layer, one node in the output layer, but I have 10 nodes in the hidden layer, okay? But same operation that I just did it right here, but it's just 10 things happening at the same time. I mean, there are 9 more of the nodes in the hidden layer. That's all. 1 in the input, 1 in the output, but 9 more in the middle. That's what it looks like here. Okay. And again, if I have 9 more, then I do have all of this that I need to train, including the output layer, which also has more weight that I need to do too. Okay. So in the end, I end up with something that's more complicated, right? So notice that this one, I do have summation. So I have to repeat this thing 10 times. It's a summation of this term, right? 10 terms of this. And now I have 31 parameters. And now it looks better, right? And for me, this is where I should stop, right? I mean, if you can evaluate something like this, then you know from eyeballing that this one probably, good to go, right? It might lack some of the fitting in the tail, but fine, right? I mean, going from now would be overkill to your compute anyway. But the thing is that you have no way of knowing something like this. Like in your actual application, you don't know. You just throw everything in. So that's why like ANN is always going to be slow, because you always overkill. Like you always come up with like the huge network, whereas you can just do something like this if you know what it looks like. You don't know. That's where the expertise come from. Like the experts know how to tune it exactly so that it's the most optimized way. Okay. I can go.
The input value x.
Yeah.
It's just like a continuous number, or is it?
This one, yeah. All of these are data points.
Just points.
Points, where just x and y is in here, right? I input everything, all of these points into the network, let it learn. We'll talk about learning later, but it learns from this data so that it can reproduce this function. Mm-hmm. I mean, if I were to replace this, the whole thing, right? I can always use the regression, the regression model in machine learning. I think we learned about linear regression, the support vector regressor, the decision tree, the random forest regressor. All of those can also reproduce something like this too. No problem at all. And I would also suggest that if you were to do something like this, right, your data is like this, you should try something else first before you do ANN, because ANN is way overkill for this type of data. You might want to do artificial neural network when you deal with something like image, language, audio, video, and something like that. But usually just normal data, like all of those random forest, gradient boosting machine, that's the state-of-the-art model nowadays.
You mean like in language translator? Or?
I'm talking about this one, right? So if you have data that are just, a bunch of X and Y, like your, I don't know, like your price of your product, like you want to do the forecasting of your price, you want to do like customer demand prediction, or you want to do I don't know, like machine learning for the shirt size, like you have age and weight and things like that. Those type of data is inhomogeneous. And the best model is actually not ANN because it's way too overkill for what it should be supposed to do. This guy, I guess the best killer application for ANN or the neural network is image. Image is what this thing cannot do well. It cannot do well, but this can do image well. And next task, sequence data, like language, like audio, like video, things like that. These guys are the best. So again, in my personal opinion, like when students propose the project, they always need to throw ANN into it. I have no idea why. Like I feel like that's the worst choice in their selection. Like I think the best choice for them would be something like here. And they never picked it. I don't know why. They just always do random forest.
So I input like points and then I get pictures by using ANN?
ANN is like, you can do a bunch of things. Like for example, image classification. Image is this one, homogeneous data. And this one's the best for image. I mean this one not the best, but this guy, convolutional neural network, is it's when people start getting more attention. Like it's when ANN start getting more attention, when it can solve image. Before then, nobody cared about AI, machine learning, right? But after image, AI just explode in popularity because it's a hard problem to solve. Like image is like crazy, right? Like how does it know? Like, how does it know this is a cat picture? It's so crazy, right? That one, you cannot use all of those above. Okay. So crazy, right? And then language, it's another thing, right? Language is even like the hardest problem, I think, nowadays to solve. And we solved it with transformer. So stay tuned. Hopefully I can make it because like, I want to do this for many, many years. That's why I skipped the large part of the lecture so that I can do transformer. So wish me luck. I'm reading, watching video, a lot of things nowadays. So it's kind of difficult for me to kind of boil down everything to one lecture. So it's a challenge for me. So wish me luck. All right, so next up, I want to go crazy, right? I can do this. Nobody can stop me, okay? So I want to do 2 hidden layers, right? The first one has 64 nodes. The second one also has 64 nodes, right? And if I were to count everything, you need to count it, but I counted already. 128 parameters for the first hidden node. So I just count all of this, all of that, sum together. And then also count all of these parameters that I need. I get 4160, right? And also there's parameters at the output layer. So combine everything, you get 4,000 parameters. And as you can see that this one started to get into the noise fitting territories. It's called overfitting. When you start to fit noise, right, as I was saying, right, your data is always going to be noisy. But what you want to fit your model to, it's not the noise. You want to fit to the signal. The signal is something that your eye can process, right? Your brain can process the trend. You want your network to do the trend, not the noise. But this one, overkill, too much, right? But again, you don't have the luxury of seeing something like this in your real projects. You're never going to know this. So it's not easy to detect something like this, right? What you're going to see is that your accuracy increases. Like this one actually has more accuracy because it, follow all of these wiggles. But that's not what you want. You don't want that because this one is not generalizable. You want something like trend, smooth function. That's what you want. But again, you don't have that luxury like this. You don't know. So that's where the experts come in. Like expert knows when to stop and when to tune your model correctly, right? Okay, and if you want to go like even more crazy, I can do deep neural network, right? I can do in one input layer, one output layer, and then that. And I have no idea why, but usually people do the multiple of 2, like the exponents of 2, like 128, 256, 64, 32. So, I mean, there's nothing prevent you from coming up with like 19 here. But people don't do that. They just do multiple of 2 for, I don't know, for symmetry reasons, I don't know. Okay? And that gives you 10,000 parameters. And as you can imagine that your network can now fit little things like that. And I would say that this one will give you a very, very high training accuracy. But I mean, think about this. If I can do with 30 parameter, I don't want to do 10,000 parameter. Like think about how heavy your model is going to be. Like when you put it in production. Like think about how long it's you have to train all of this. This one actually takes a long time to train compared to the 30 parameter that I had way before. The training time vary 20 times before like 30 and 10,000, right? So that's something that you don't, and then you have no idea what happened like this in your real application. You have to look at other metrics like loss, look at the accuracy per time, per epoch, and things like that in order to know what happened. Okay. All right. So fine. Okay. So I just show you that the architecture does matters a lot. And then there's some, you don't always want to go to the most complex architecture. Right? So what is it? So the rest, there are 2 things that I need to talk about. First, what it's doing when it's predicting something. So once you have the network that is already trained, what's happened when you want to predict something, and then what happened when you want to train something. And that is a building block for the rest of the lecture that will come. Okay? So let's think about the network that has 2 hidden layers. Okay, and I'm doing sigmoid activations, right? So there are 2 hidden layers here. Okay, and then let's say that I already trained my network. So I'm going to initialize the weights and biases. So I'm going to use a real number so that you can kind of follow along. So this one I just came up randomly. Normally you should have something that you know, like not in a perfect integer like this. And then let's see if I have observation. So that means that if I were to input my x here, input here, then I expect that my output should be somewhat close to 10. Okay, so that's called the ground truth, for example, essentially. Right? How are we doing on time? Let's see. Okay, so an hour, so that we're fine. You're fine, right? Let me know if it's too. You need some rest. Okay, okay. It's get a little bit heavier. Okay, not heavy. Okay, all right. Let's go. First, I write everything down in here. Okay, start from the top left, the input. Okay, so first I'm gonna input 1. This 1 come from here. Right? I just know that if I input 1, the actual ground truth is y equal to 10, right? But I don't know what this network is going to predict. I want to see how it's doing, right? So I input 1 into here. So first, the input network do absolutely nothing. That means that this 1 will get into 1 here. This one doing nothing here, okay? And also this one will do absolutely nothing. So that's why I get 1 out. So the input node is just almost like a placeholder for the library to know the numbers of input. Okay, next up, I'm going to go to the first hidden layer. Okay, so here, the first hidden layer is a combination of the input and the weight plus the bias, right? Input is here. Input, the weight plus the bias. If I were to plug everything in, that means that my input is here. Sorry for the line. Input is here, okay? The weight is here, and the bias is here, right? And I do have all the numbers here, right? I have 1 and 0 as the weight and the bias. So that means that in the end, I do have this equation here. I'm just plugging all the number, right? And then in the end, I got 1 out. I mean, unsurprisingly, but I mean, it can be any other number. It's just 1. right? Nothing, I just multiply plus the number, that's all. Or you can take my word for it, right? If it's getting too hard to track, just take my word for it. I'm just plugging the number in. Okay, so I get ones in here, okay? My one, the number 1 become an input to another nonlinear function. This is the activation function. It has a form of the sigmoid function, okay? So I'm supposed to plug my inputs in here. So my input goes in here. Okay, that's why I'm writing it like this. Okay, and then in the end, I got 0.731 as the output. Okay, so, but because this hidden layer is connected to 2 nodes in the other hidden layer, I need to copy my output to all of the nodes in the next layer. That's why there are 2 things that goes out, right? It's the same number, but I just need to copy all my output to the output to all the nodes in the next hidden layer, right? These 2 guys are in the next hidden layer, so I need to supply them some value in the end. That's what I'm doing. Okay, so 073 will become the input to these 2 guys right here, and now the next round continues. Let me know if I'm going too fast, okay? But, or you can take my word for it too, if you trust me that I'm doing it correctly. Okay. All right. So we're going to go through the first one. The first node, again, the input will go through the linear function. So that means that you're gonna multiply the input with the weight and add it to the bias. So that's what I'm doing here. 2 times 0. So this is the input. Okay, let me do it. Input, the weight, and the bias. Where did I get it from? I get from this one here, 2. My 2 is the weight. I came up with this value randomly. Nothing special about this number 2 right here. Okay, and I got 1.462. So that's what I'm writing right here. 1.462. Okay. I do the same thing with the next node in the same layer. So that's going to be 0.731, so right here, times the weight. This is the weight coming from here. This is getting crazier, so let me just remove this, okay? And then add it to the bias, which is 0. Okay, I got 2.13993, and I'm writing it right here. Right? It's just a step and then a step and in a sequence, right? Okay, next up, all of this input goes into the sigmoid function, right? I putting 1.462 in here, and I put 2.193 in here. And I think it's just get too crazy, so I didn't write it out, but take my word for it. It's going to be 0.8 and then 0.899 as the output, okay? This one only need 1 output for each of the node because these 2 guys are actually connecting to the output node, which only has 1 output. If these guys are connecting to the network that has 2 output nodes, let's say if I have another output node, then the first node in the hidden layer will actually have to copy the output into here too. Okay, just want to let you know that that's how it works. And also this node right here needs to copy the output to the second node in the output layer. Okay, and if you have more, then the output's going to be copied over so that they're all connected. Okay. Okay, but this one is simpler. So first circuit, we're almost done. Next up, the output node, since it's connecting to the 2 nodes from the previous hidden layer, it also has 2 weights. Weight number 1 and weight number 2, right? So what happened is we're going to do the multiplication of weights number 1 and the input from the node 1 per se, and also the weight number 2 multiplied by the input number 2. And then adding to the bias, which is 0 again. Okay? And I'm going to get 7.745 as the output from the linear part in my output node. Okay. And then the next stop is the activation function. But luckily, there is no activation at the output node. It just copies the number out. So all I need to do is to output 7.745 to here. And that, ladies and gentlemen, this is my prediction from my neural network. Okay? And as you can see that the math is simple, but the things that make this one powerful is the architecture. If you have more things in here, then the number just get multiplied and addition into the crazy equation. I guess crazy sequence of calculation. It's just a lot of simple calculation chained together in a nested way, I would say. That's what makes it so non-linear in the end. But that's all it is, guys. There's no magic in this. And once you get to know all of this, you're going to trust AI less and less because it's just math. Like how much, it depends on the guys who train them, that's all. It just depends on the way that they're trained, just math equations. There's no, when I hear about, general artificial intelligence, like AGI, right? I'm just kind of, I don't know, I feel like this is just equation. Like how does it have life on its own? Like you might see some paper that say, like ChatGPT start to think about, has its own, intelligence, its own conscience. And I just feel like this equation is just going to have its own conscience. Like it seems impossible to me. But I could be wrong, because I was wrong about it, a lot of times, right? Like I didn't even think that ChatGPT would happen like 5 years ago. So I was wrong before, so I could be wrong again. That could be like AI taking over the world for real. I don't know. Yeah. Okay, but I digress. So as you can imagine, this is my prediction, right? And if this is all you do, fine. You have to trust your network that this is the right value, right? But during the training, right, we actually know that our model is bad or not. Because think about this. If this is the training data, right, we know that there is, the network supposed to predict y equal to 10. But then during the training, if I were to pass the 1 into the network, I get 7.745. So there is an error. Like if I can find out what the error is, I can train the network. And the way that you're training it is the same thing as we did always. This one, optimization. We are doing the optimization problem to reduce the loss. With respect to all of this variable, like all of this has to change, right, somehow, in order to minimize the loss. Okay? And the loss is essentially how bad our model is. This is not the new concept in any shape or form. This is the same thing we did since perceptron. How do we quantify the loss? In artificial neural network, it's the mean squared error, MSE. Okay, so you just do subtraction of your prediction with the ground. Oh, sorry, prediction is here. Your prediction, how far is your prediction from the ground truth? And then you square them so that you don't get the negative number. That's all. Okay? So in our example, our network has the loss of 5.082. Okay. I want you to keep this number in mind, and we're going to train our network in one epoch. And we'll see what happened to our loss. Okay? And I think this is a good time for you to get some rest because the next one is going to be a little bit more involved. So take some rest, come back fresh, and we'll deep dive into back propagations. Okay.